All right, thanks everyone for coming. I'm very pleased to introduce our two speakers today. It's two for the price of one. I think Chris is going to be starting today. So Chris Mann is a research assistant at University of British Columbia. I just learned that Chris actually got his bachelor's degree in psychology before he transitioned into astronomy. He's now finishing his master's degree, working on this project with Harvey. So after we hear from Chris, we will hear from Harvey Richer, who's a professor at University of British Columbia, bachelor's from McGill, PhD from University of Rochester. Many of you may know Harvey already. He's no stranger to Gemini. He was on the Gemini board of directors from 2000 to 2003. He was on the CFHT board of directors for 7 years, 2006 to 13. Harvey is here spending the month in Waimea at CFH, and he was gracious enough to come down and tell us about what he and Chris are working on. So, thank you.
Thank you very much for inviting me here. It's about the best business trip I could hope for. Follow Harvey to Hawaii. So the project I've been working on for, I think I started it in an undergrad thesis and carried on to it for my master's thesis, is looking for an intermediate mass black hole, particularly in the globular cluster 47 Tucanae. And as a sort of rough idea, if you're not familiar what these objects might be, we all know stellar mass black holes. These are the things that form when massive stars evolve normally. It's the end of their life cycles. And then we all know about supermassive black holes, millions or billions of solar masses found in the cores of most galaxies. But there's a conspicuous absence of something in between, sort of 10 to the 2, 10 to the 5 solar masses of black hole, these intermediate sized ones. And it's really hard to explain where the supermassive ones come from without presumably coming through this intermediate phase somewhere. So the sort of proposed formation mechanisms generally point towards needing a very dense stellar environment to form them. And they've not been found, they've not been verified. There's a lot of hints, suggestions, upper limits, but no clear findings thus far. So the centers of globular clusters provide these really dense stellar environments where you might find such objects. So this is a project that I've been working on. There's a slew of summer students as well in the orange, and then in the blue we have some more senior research staff, and some at UBC, some elsewhere, that have certainly been helping along. So the data we have to work with is much like what you see here. This is the photometry of the center of 47 Tucanae. So it's a really dense core. However, our images are extremely good. We have HST data from a couple different epochs, roughly a decade apart. And so using the decade transition of data, you can get proper motions for all these stars. So we have proper motions of around 50,000 stars in the core of the cluster, and a dozen stars or so right in the central arc second, where you expect the kinematic signature of such a black hole to be most evident. So this is a big step forward from using a lot of these radial velocity studies where you might get a few dozen stars to work with, not necessarily in the crowded center. But we're able to sort of bypass a lot of the problems you find from looking in these dense regions because our filters are very blue. We have 225, 336 are ultraviolet filters, and the earlier epoch is 475, which is a very blue filter as well. And this is sort of a twofold bonus that we get from using these types of filters. One is you just get a much tighter diffraction limit just from using the short wavelengths, but secondarily, these blue filters are really suppressing red giant light, which is very dominating in the center. They just sort of wash out your picture. It's hard to see the very sort of intricate work goings on right in the center because you just have a couple massively bright red giant stars that are really suppressed in these filters. So it doesn't actually show up terribly well on this screen here, but this is an extremely high quality photo. I think our collaborator Jeremy made like a several gigabyte picture of this cluster core. It's amazingly beautiful, but we really do get images right down to the center. And so these are the proper motions that basically we'll be doing the kinematic studies with. And so if you're unfamiliar with 47 Tucanae, it's a southern sky globular cluster. This is the SMC, Small Magellanic Cloud, and 47 Tuc is, sort of sequestered just off to the side. And often that can cause some problems because you get a bleed over of SMC stars in the background. There are ways to get around that. I'm happy to answer those questions in the Q&A session at the end, but for this presentation, I've skipped through a bit of that. But we can talk a little more later. But what we aim to do is sort of get an idea of how the velocities are behaving in this cluster to see if something at the center, if you require an extra massive black hole mass in the center to describe what's happening to these velocities. And so we start with a King model. This is the density distribution. This A parameter just gives you sort of a typical size of the core. That's where the densities start to drop off significantly. And so we can fit for this parameter based on the densities, and you get just under 40 arcseconds. This is kind of how big the core of this cluster is. And we're using something called Jeans model fitting, which this is the isotropic Jeans equation. So it's kind of a gas dynamics equation. It relates sort of the densities, the velocities, and the potentials that they're in. So we get a gravity term, which is the potential of, generated by the stars themselves. And it influences this sigma term, which is the velocity of dispersion. So you get a squared value there. And that's what we're interested in looking at. And also this M, which would be, M as a function of radius. As you go further out from the center, you enclose more mass. When you put that into sort of terms of including a black hole as well, you get a little delta function in the center, where there's a big super concentrated mass in the center and then the smooth distribution outside of that. And so we can use this equation, solve for the sigma squared, and you get a velocity dispersion. However, this is a 3D space. This is a theoretical calculation, whereas we view everything on the sky, 2D velocities. So we just integrate along the line of sight, and you don't need to worry too much about the integrals, but that's the process that we're doing. So we get this sigma as a function of projected radius of what it looks like from our position. So you end up getting curves that look something like this. The two top ones, the red and the black, this is before correcting for the projection on the sky and after. So it washes out this signal a little bit, the projection, and then the two bottoms are sort of the cluster term. So there's two terms in this equation, the black hole term and the cluster term, and they will be added together sort of in quadrature, so with different weights, and the weights would be the mass of the cluster and the mass of the black hole. And that A parameter kind of sets where this fall off happens, and then there's the tidal radius where the galactic potential is basically truncating where the cluster goes. So I've artificially put in a huge mass here for the black hole, and that's it sits up really high, but it will in actuality be much smaller than the mass of the cluster. So we can try and fit these curves to the velocity dispersions. However, there's a caveat that we want to think about before just sort of blindly fitting these curves to the data, and that is we have a sample of stars. I said we have 50,000 stars. That's a pretty good sample. We think we've got a pretty good idea of a pretty representative population of the stars. However, when you use photometry, you're biased towards seeing the bright stars, which are the massive stars. They are not the majority, right? So the few bright stars dominate the light in a cluster, but the many dim stars dominate the mass, and those are the ones you're not quite as sensitive to. And then you have something called mass segregation, where it's an equipartition of energy. Heavy stars tend to scatter off light stars as they dynamically interact, flinging the light stars to higher velocities and the heavy stars to lower velocities. And you concentrate heavy stars in the center, and you sort of fling light stars out to the side. So if you were to take a certain massive star, it will have a different sort of core parameter, how concentrated these stars are in the cluster. So in order to sort of allow for that, if we didn't have a quite representative sample, this A parameter, the core parameter in that King model, we split that into sort of the proper motion. We call it APM. So that are tracer stars, those stars which we have proper motions for, and that A parameter goes into some terms of those Jeans equation that is based on sort of the velocities that we're seeing. But then there's this cluster A, which the terms that are generating the gravity, which are forcing things to move in certain ways. We may not be seeing those, but we will be seeing the effects of those. We won't be seeing those stars. So it's just a parameter that we allow. And so instead of those, nice simple curves that you saw earlier, we have a bit more complicated surfaces where, if you ignore this axis here, it looks just like it did before, but now we can change sort of how, if this HCl over APM was 1, that's what you saw before. They were identical. We have a perfectly representative sample of the stars. However, it changes the shapes of the curves just a little bit by allowing these to shift. And we don't expect it to be a big change. So we're just sort of allowing that freedom, and we'll see if it actually panned out in the end. So I'm sure you'd all like to see what the data look like. So this is just sort of a simple binning system where it's a logarithmically spaced bins. So you choose 2 R values, find all the stars between these radius from the center, and figure out the dispersion in their velocities. And that gives you a value on this graph. And so as you can see, it's noisy in the middle when you don't have terribly many stars per bin. It gets much sort of more well-behaved in the outside when you have thousands of stars in each bin. And you can see that it's dropping off just like our curves were before. But the question is this significantly rising in the middle, or is it staying flat? If it were flat, that would indicate there's no black hole sort of pushing the velocities, spreading the velocities around. If there is a bit of a rise in the middle, that would indicate something is there pumping things up, ready to go. So what we could do is simply take those curves, do a least squares fit. We have some bootstrap error bars here. That's a simple thing to do. I set the summer students on this for a while to see what they could come up with, and they figured out that actually their choice of bins here. So I just said these are nice logarithmically spaced bins, but if you make them just a little bit bigger, all of these points jumble around a little bit because you have different stars in different bins. You make them a little bigger still or a little smaller, it fluctuates quite a lot. And the fitted parameters we get, the mass of the cluster, the mass of the black hole, this core parameter radius, are not stable at all. They've changed quite wildly. And I have a figure we can bring up in Q&A if you like. So we don't really like this bin fit method. It's very subjective to what bins you chose, and there doesn't seem to be a good way to pick the best set of bins. There's no best one out there. It's just the one you chose. So we were using an unbinned likelihood analysis, which I think, was it Ryan who came up with it? So Ryan Goldsberry was another student of Harvey's who's since graduated and moved on, but he had this system of unbinned likelihood, and you basically take every single data point weighted against its probability of being drawn from a curve, which is telling you about the dispersion of velocities. So if you find one that's well off of the curve, that would have a low probability of happening randomly. The problem with that is it's hard to visualize the probability of each individual data point. So I will leave this binned data there because it shows you how the velocities drop on the outside, do something in the middle that maybe rises, maybe stays straight, but that's a visualization tool. We are sort of using this unbinned system. And so you get something that looks like this. These sort of grayish flat lines, those would be, we've forced the black hole mass to be 0 and made the fit to the data as best we could. And then these different curves you're seeing are either, the top ones are this unbinned system, the bottom ones are the bin system. So you see by binning the data, you're taking all the stars in a certain radius bin and treating them all as sort of one data point, and that washes out some of the signal, this radius dependent signal. So we actually were expecting it to be a little lower, and it is. And then there's actually 2 lines almost on top of each other for each of these sort of types of binning or unbinning, and that's whether or not we allowed the core parameters to be separate or force them to be the same. So whether or not we thought we had a perfectly representative star sample or we were allowing some freedom. And there's a small difference. So this was kind of what we expected, and we also found that it made very little difference. Our stars were more or less representative, and we are right in the core. So the segregation is not, we're not seeing right out to the edge where you see a lot of the smaller stars pushed out there. So this is the curve that we're sort of more interested in. This is the we're allowing some freedom for these core parameters to change, and you also are weighting every single data point instead of binning it into the 30 data points you see here. So you have 50,000 data points to work with. And the number that's coming out of this fit is just over 4,000 solar masses, which is a pretty exciting number to see. The cluster mass is coming out at 1 million solar masses, which is maybe a bit heavier than some literature values would suggest. It's not so, I think the number is about 750,000 solar masses is sort of the idea of how heavy, how massive the cluster is. However, our models, our data points stop at 120 arc seconds. So this King model we fit, our model thinks that the King model is extending out to the tidal radius, whereas, so we're not terribly sensitive to the outer reaches of the cluster. So we figure the cluster mass may not, this is not a very unreasonable number for the cluster mass to be have spit out to us. And then this core parameter was 40 arc seconds, which again, we said was close to that 38 we measured in our tracer stars. So this was pretty exciting. We have some numbers to work with. The question now is sort of how good is our model? You can fit a straight line to curve data. There will be a best fit line for it. Doesn't mean it's a good fit. So you can do, it's sort of a bootstrapping method. We're generating false velocities based on a curve. So we had this best fit curve. You see it was rising in the center. That is the dispersion at every radius. So that's kind of the width of all the velocities. If you were to do histograms of the velocities in that radius, that's the width that they're being drawn from. So we take every radius value of every 50,000 stars and we assign a new X velocity and a new Y velocity based on randomly drawing from the width of the curve at that point. And so you do that for every 50,000 points. You now have a new set of velocities and you do the fit to that. And then you repeat this 100,000 times. So you start to build distributions. And these are the likelihood values. And so the numbers themselves are not terribly important. They can be scaled and shifted, but the distribution around the value we found shows that the value we found is very close to the peak of this distribution. And now I always trip over this, so I'm going to read it directly from my notes. We would expect to draw data from our best fitting model that differs at least as much from the real data, at least as much as the real data do from that model 88% of the time. So our data matches the model very closely, and you would expect as deviation as far as we see from the model 88% of times that you try this experiment. So it's very consistent. The model is very consistent with the data. It's by no means out in the fringes. It seems to be a very good fit to what we're seeing out on the sky. And then we can sort of do the similar things where now instead of the likelihood values that we get from this likelihood fitting, we have the resulting black hole mass, the parameters, the fit parameters that come out. So we've resampled all the velocities, and you fit a new curve to these velocities and see what black hole mass you pull out. And so we were inputting 4,100 solar mass model, drawing velocities off of that model, and these are the black hole masses we get out of it. So the black line and the yellow line, or what we were finding and the mean of this distribution are basically on top of one another. So we are, with great fidelity, our model is pulling out the number that we put in, even through this random noise. And the zero is sort of 3 sigma away from this mean. So if you were to draw velocities from this model that has the black hole, it would trick you into thinking there's no black hole right by random chance, with, what's that, 97%, or 1 minus 97% of the time. And then you can do the inverse of that. So we can force a zero mass into the model. So it's a perfectly flat model, fit it to the data the best you can, and say how often do the randomly generated velocities just happen to be up in the core enough to trick you into thinking there is a black hole. And this is basically like that last picture shifted to the side, where now the 4000 is, beyond 3 sigma in the other direction. So you don't get tricked into thinking there's this black hole off of this model very often as well. It's 0.05% of the time. This spike in the middle, I was noticing as I was putting these slides together, seems to be a fitting artifact. I suspect whatever the code was doing didn't like a slightly negative, which is allowed in the model, black hole, and instead used a slightly positive. I've yet to figure that out. That will be my next task. But so just to wrap up, and I'll let Harvey sort of continue with his presentation. We can exclude this absent black hole to pretty high confidence. So both of those graphs show beyond 3 sigma that there seemed to be something there. And the model is coming up with a sort of 4,200-ish black hole, plus or minus, and the widths of those distributions are about 1,300. And so this unbinned likelihood analysis just seemed a very useful tool to avoid the intrinsic random biases of binning. You choose your binning system, and it seems to fluctuate wildly if you chose a different binning system. So this has been my life for the last little while. We've been sitting on a paper because problems keep popping up and you got to fix them. But I think we're getting close to putting it out there, and I will also turn into my master's thesis as well. So thank you for listening, and we'll definitely take questions at the end of Harvey's talk. I think we'll do them all at once.
Is that what you want to do, Andrew?
It's up to you, whatever.
Okay, I'm happy to answer if somebody's got questions now.
It might be easier if we take.
Probably better. I mean, since it's fresh,
Okay.
people want to ask questions.
Are there any questions for Chris? Including anybody off-site?
I have one on the back.
Yes, me. My question is, there are confirmed stellar mass black holes in 47 Tuc, correct?
In the cluster, there's X-ray sources, X-ray binary sources, I think.
There's neutrons. There's lots of neutron stars.
Okay, so no stellar mass black holes.
Don't think there's any solar massish black holes that are known.
Are there X-ray binary sources in?
Yeah,
47 Tuc?
lots.
So those are black
There's
holes. aren't
25 pulsars known in
Okay.
they? They're there. We're pretty sure. And it's hard to
Yeah, I'm
believe that
just
they wouldn't
wondering
be.
how would the population of dark remnants inflate the dispersion?
Right. So it's certainly possible that because, like I mentioned earlier, the segregation effect that massive dense objects tend to sink towards the center, whereas the lighter objects are flung towards the outside. These black holes would tend to sink towards the center. So it's not necessarily I don't think our method here is sensitive to a cluster of small compact objects versus one point source object, as long as they are close enough.
Right.
The model I'm working, it's sort of in the sort of the logarithmic R space. One more. This keeps rising in the center because we have a point mass. You get arbitrarily close to it, but if it were not a true point mass, as in some distributed mass, it should flatten out at some point, I would guess. Mm-hmm. However, you have very few stars once you get really close to the center. So I'm not sure we're terribly sensitive to that if they're quite compactly swarming, but it would probably flatten that curve a little bit. Would be my guess. Good question. Anyone else? Anyone who's listening online as well?
Well, I guess I have another question then. I guess you've seen the HST promos profile.
Promo?
There's this project, Proper Motions from HST.
Okay.
It's a paper by Watkins.
Is that recent? I don't know.
2015, I think.
Okay. Maybe you've come across it.
Oh, well.
Names and dates are not great in my
Just
head.
that they derived the profile for about 20 different globulars.
Okay.
One of them was 47
Yeah.
Tuc, but they do fit a flat profile right in the center.
Mm-hmm.
But of course, they're using binned data.
Yeah.
Sorry, this is Watson et al.
Yeah.
This
No, Watkins.
Watkins, yes.
Yes.
Okay.
But they're using binned profiles. I was wondering, what was your opinion on that paper? But
so this is something I had saved for the Q&A, and perhaps the numbers on the side are not this was an older plot put together by the summer students, and I didn't have their code to recreate it immediately when I was putting this presentation together. But the idea is right. So this is a bin size scale factor. So we chose some sort of fiducial bin size, and then we scaled each of the bins bigger and bigger, bigger, smaller, smaller. And this is what was happening to these parameters with small changes in bin size. Like it's, jumping 1,000 solar masses from our fit parameter. So as soon as I saw something like this, any hesitation I had about using the likelihood fitting evaporated, because you don't have to deal with choosing the right set of bins. Right. I think if you had a super good data set with the more stars you have, obviously, in each bin, the less they will fluctuate. But I think our data set is as good as any out there and better than most. I can't imagine you'd have so many stars in the inner bins that you wouldn't see fluctuations based on your choice.
Yeah, because their catalogs are optical, actually. So there's completeness in the center.
Yeah, the crowding in the center is a very difficult thing to get around in the longer wavelengths.
Yeah.
The stars just blend together, and the red giants also.
Yeah. The fact that you guys are using bluer wavelengths really, it's
which I think this is some of the first very blue data sets in the core.
So. Yeah. But it's interesting that even still, no bin can account for a no intermediate black hole.
Yeah, that's true. There's so doing the literature searches I have, there's a lot of varying ideas out there. And who was it? It was what was the big controversy in Omega Sen? Was it?
Omega Sen was an issue.
And
about the center, where the center was.
Where the center was, it was.
There's a big literature about IMBHs.
Yeah, and, there's a lot of
there's a lot of positives, there's a lot of negatives. It's really a subject which I think is still in a huge state of flux. People who did spectroscopy, for example, found very evidence for a very large black hole in Omega Sen.
Yeah.
And then the people, Jay Anderson, for example, who's the guru of proper motions, he looked at the proper motions in the core, and it was just the dispersion was just flat right into the center. So there's this controversy. I think if you're doing spectroscopy, you have a much harder job because you have to disperse the light and so on, and the crowding is enormous. So.
Yeah, and the flux will be dominated by the brighter stars. So you introduce another bias. Okay, thank you.
Thank you very much. Can you stop sharing?
Yes.
So I want to share screen.
You gotta wait till I end mine, and then you can. I don't see the stop share button. I can unplug. No, I could probably just close the software here. View meeting. There we go. That should do it. Okay. Thank you again.
Okay, so I want to just spend a few minutes just talking about some very personal ideas about what JWST is going to do for globular cluster research. And some of this is based on an early release science proposal that we have in, and maybe we'll get time or maybe we won't get time. We'll know in about a month or so. But just to give you an idea of some of our thinking about what you can do with JWST that could really change our ideas. So here's a slide which gives you, and I'm sure most people are familiar with this, gives you an idea of what these telescopes, what their sizes are and what their orbits are like. So HST is sort of a smallish telescope, 2.4 meters. And Hubble, JWST is significantly larger. Hubble orbits around the Earth, so you lose a third of your orbital time roughly when you get too close to the Earth, and you can't expose. Whereas JWST is at I don't think this doesn't work against the light, does it? Okay. is at L2, and you don't have that issue. And then there's the spectral sensitivity, the coverage. Hubble goes down into the ultraviolet, down to almost 200 nanometers, and out to H band 1.4 microns. And you can see that JWST is going to go from the optical out into the far infrared at about almost 40 microns. So they're really quite different telescopes, and their capabilities are will be very different. So just to let you know that JWST can survive even me. So here was this terrible tornado that hit Texas last month. Here was a little picture about what it looked when it came into Houston, and the incredible flooding. But it was nice to know that JWST was in storage when Harvey hit. It was not damaged whatsoever, and it apparently emerged completely unscathed from the storm. So that's a very good thing. A very bad thing is this. It did not survive delays in the instrumentation integration. I'm sure most people know about this also. So it was originally set for October 18 launch. It has now been delayed and will be launched sometime between March and June 2019. So that's a big disappointment that it's another 6 or 8 months or so. The claim is that no new funds are required. That may be true, but that was one of the issues that was funding. There was a very tight deadline for October, and there will be no new funds available, so it has to be done within the existing budget. At least that's the current idea. So just to get an idea about this is probably a slide that most of you have seen. This gives you a really nice idea of why Hubble was such a spectacularly good telescope, and tells you why JWST will also be a spectacularly good telescope. So you can see that in the optical, very near infrared, Hubble was almost 2 orders of magnitude better than the best of the ground-based telescopes, and that's why it achieved an enormous amount. And you can see that JWST, certainly at least in the near infrared, is going to be 2 orders of magnitude or so better than the best ground-based telescopes out into the several micron region. So the expectations for Gemini are enormous because it will have this tremendous sensitivity compared to ground-based telescopes. And here's a little indication of what one of the major imagers with JWST will be capable of. This is NIRCam, which goes out to about 5 microns. And here are all of the sort of specs that it has. And the field of view is sort of like Hubble, but it's of course way far into the infrared, and it'll be a spectacularly good telescope in that spectral region. Well, let me talk a little bit about some science that we're hoping to do with this telescope. So one of the things that I personally am really interested in is looking for debris disks around white dwarfs in globular clusters. Now, we know that lots of field white dwarfs have debris disks around them, and they show up as, in the simplest way, via infrared excess, and I'll show you an example of one in just a second. But the main idea is that the model for a debris disk is a disruption of a moon or an asteroid when the host star becomes a host planet, becomes a red giant. So the idea of the existence of a debris disk around a white dwarf tells you that there was probably a planetary system of some sort around that, around that object. So if you can actually detect the infrared excess in globular cluster white dwarfs, globular clusters then would have had planetary systems in it, and who knows, an early rise to life in the universe might be possible. So I think it's a very exciting area to look into. This is the sort of the poster child for what a debris disk around a white dwarf looks like, GD 2938. And here's the white dwarf spectrum, completely white dwarf spectrum, down to about H band. A K band, maybe a hint that there is a debris disk. This is the HST wide field camera 3 limit to the H-band. These are from a number of quite small space instruments, but you can see there's this enormous infrared exit. As I said, this is the poster child, so this is the best example. There are no others that look as good as this. But here's the near cam limit at about 5 microns, and you can see that's easily detect the disk with that telescope. And here's the MIRI limit at about 30 microns. And so you could detect this infrared excess easily with an instrument like JWST. It's been detected with smallish telescopes. So that's what a debris disk will look like in the infrared around a hot white dwarf. So we've actually been looking for these for quite a while now. About 5 or 6 years ago, we had a very deep exposure, 120 orbit exposure in 47 Tuc in this region over here, and I'll show you some of the data for that to look at the end of the white dwarf cooling sequence. But we did parallel observations with this is with ACS, with 3 in a region around here in 4 colors, 336, 606, 110, which is J, and 160, which is H. And so we found lots of things, lots of white dwarfs, of course, were found, easy to find in the 2 bluest filters, but we also had the more infrared filters for these objects. And here's one candidate, and I have to say it's the best candidate. One candidate that we found, and this is the spectral energy distribution of that one candidate. It's a 22,000 degree white dwarf. Its spectral energy distribution ought to look like this red line that you see over here. And it sort of fit that in the 3 bluest colors, but in H-band, we saw a large deviation. Now, you don't want to bet the house on this for lots of reasons. There could be contamination. The point spread function is pretty big in the infrared with Hubble and so on. But nonetheless, there is an indication of this with the Hubble data. We actually put in applications to Gemini. Andrew was a collaborator on this to try and observe this in K-band. We were given 10 hours in band 2, which was a complete waste of time, I might say, because we needed really good conditions. And it's in 47 Tuc with not a lot of visibility. And we got 10 minutes out of the 10 hours of exposure time. And so that did nothing for us whatsoever. But that I still think is a good project for a telescope like Gemini, but it'll be blown away when JWST becomes available. So that's one project. The other projects that I want to talk about are various ways to talk about ages of the oldest stars in the universe. And here's a bunch of reasons why old stars are interesting. It pushes up against cosmological results for ages. It used to be that the oldest stars, when I was a kid, the oldest stars were older than the universe. And that was because there was errors in the isochrones and so on. But the oldest stars were 17, 18 billion years old, which makes for a very interesting universe. But that all got eventually resolved. But here's a number of reasons why measuring the age of the oldest stars are important. So what can JWST do for you? Well, here's an example which we actually got from HST. This is the color magnitude diagram of 47 Tuc in some of the broadest filters that we observed, the broadest wavelength range that we observed with Hubble, 390 and F160, which is H-band. And you could look at, you could see the scale here. I mean, we have 7 or 8 magnitudes in color along the along the x-axis. This is the color magnitude diagram of 47 Tuc. Remember that the SMC is in the background, so this is the SMC in the background. And here's the white dwarf cooling sequence in 390 and 160 in these filters. And there's lots of things that you can do with this. For example, because we've stretched the color magnitude diagram so much, If you wanted to fit isochrones, for example, you have a lot more sensitivity to fit isochrones in a big color range like this. And I'll show you what this might look like with JWST in a moment. To select the binary sequence, you can see how nicely the binary sequence jumps out down the main sequence when you have a big color range like this. We can select the white dwarf cooling sequence here, and we could look for infrared excesses, for example, along a sequence like that. And I'll come back to brown dwarfs in just a moment.
Let me push the button over here.
Sure. Okay, so this is just what the main sequence turnoff looks like in a couple of JWST filters compared with the typical filters that we use for turnoff ages with the ACS. So this is the ACS filters, and in the red are just 700 nanometers versus 3.2 microns, and you can see how stretched the color magnitude diagram is, and there'll be a lot of more sensitivity. In fact, your sensitivity to age is at least twice as good with the near cam filters. And there are. Whoops, let's go back here. Okay, so one of the things which we use to determine what globular cluster ages, something we've been doing for the last more than a decade and a half, is to look at the cooling white dwarfs, find out what the coolest white dwarfs, what their temperatures are, and that can provide an age. And this is a little idea of the background behind what's going on here. The white dwarfs, these are cooling sequences for white dwarfs of various masses. And remember that the low mass stars are above the high mass stars because low mass white dwarfs are bigger than high mass white dwarfs. So at a given color, they'll be more luminous. So for example, if you find a white dwarf that has an absolute magnitude of 14, and you know that it's 0.6 solar masses, well, you know that the age of that white dwarf is about 2 gigayears. And in this way, you can actually measure ages of white dwarfs. And in some sense, this is a much better way than trying to get ages from the turnoff, because if you take a look at the color magnitude diagram of these two clusters, and I ask you, for those that are familiar with stellar astrophysics, which of these two clusters is older? So Andrew, I'm going to put you on the spot, and I'm going to ask you which of those two clusters is older?
The black one.
The black one is older, and that's because the turnoff is at a lower luminosity. And Andrew should be right, but he's absolutely wrong. And the reason that he's wrong is that there is a huge metallicity difference between these two clusters. And there's a huge age metallicity degeneracy when you look at clusters like this. So this is 47 Tucani and NGC 6397. 6397 is much more metal poor. So you have this degeneracy, which you really have to understand really well. The nice thing about white dwarf cooling is you get rid of this degeneracy. And the reason for that is the metals in the very dense atmosphere, or the very high gravity atmosphere of a white dwarf, they settle out. So all you do is have hydrogen and helium in the atmosphere, and the metals are gone. So although the main sequences may be set off quite a bit by metal abundance, the white dwarf cooling sequence is not set off by metal abundance, and they actually lie smack dab on top of each other. And all you have to do here is to look which one has cooler or fainter white dwarfs in it, and you can see it's the red one. So the red cluster is in fact older by about 2 gigayears. And this is one of the ways in which we've been measuring white dwarf ages. Okay, so they're good plots. White dwarfs cool very nicely, about 1.6 degrees per million years. And so we can use them to measure ages in the way I've just described. And here's some Monte Carlos of some white dwarf cooling sequences. And you can see that the fainter ones are quite a bit older. And here's one of the results which we've come up with thus far, with basically the age metallicity relationship for globular clusters. And it looks as though these are halo clusters. This is a bulge cluster, and this is the thin disk. We also measured the age of the thin disk from white dwarfs. And you can see that there's quite some evidence for an age-metallicity relationship. But these are all the clusters that one can do with Hubble. There's actually one more we have time for this round, but that's going to be it with Hubble. You won't be able to do any more clusters. They're just too faint. But with JWST, we have planned out this program. It's only 260 hours of JWST time, which we can do the entire age metallicity relationship in detail with a study of just 11 clusters. So that's a program which we hope to do at some time in the future with JWST. The future may look a little better than that. It may not be necessary to look at two clusters and construct the color magnitude diagram, because you can see here when you get fainter than some magnitude, this is again 47 tuck, but when you get fainter than some magnitude, you're dominated by the white dwarfs. In fact, the white dwarfs are the only thing in the cluster. That's not quite true, as I'll show you in just a moment, but it's true to a first approximation. So all you have to do is look in one color, proper motion clean it so you know that you only have cluster members. This is the main sequence, which dies at some point, and then the white dwarf cooling sequence pops up, and where the peak in magnitude is of the white dwarf cooling sequence, that'll be an age measurement. So that's something you can do. The white dwarf peak just gives you the age of the cluster. Do I have a few more minutes, Andrew? Because I wanted to do one last thing.
Yeah, sure.
Yeah, okay, good. Okay, I just want to talk about something new we've been thinking about in globular clusters, and that's looking at brown dwarfs. These are objects which are of great interest. They're obviously the link between stars and planets. In a survey of the literature, it's not clear how these things form. People are not quite sure how they form, whether they form like stars or whether they form like planets by accretion. But the thing about white dwarfs is after they form, they never ignite helium in their core. So they just continue to cool and cool with time because they have no strong internal source of energy. So again, they're an age diagnostic. The cooler they are, the older they are. And let me just show you a few diagrams that we've come up with on this. So this is 47 tuck in the optical. I know it looks a little bit messier than what I showed you before, but this is 47 tuck in all its glory, down to very faint magnitudes that we did with HST. The blue are the objects when you proper motion clean it that are clearly cluster members. The black things are different. We get down to around little lower in mass than around 0.09 solar masses from the ACS observations. But you expect, this is a model, you expect data all the way down here. And the real bona fide white dwarfs start over here. These stars are trying to sort of decide if they're going to be brown dwarfs or they're going to burn hydrogen, and they're on and off a little bit. But the bona fide brown dwarfs start at around 0.08 solar masses. These are completeness, by the way, in case you're interested in the data which we did with ACS. So this is what models look like for very low mass stars. This is luminosity versus age. So if you're not a brown dwarf, then you will contract and get fainter and fainter, but then you will continue to burn hydrogen basically forever, and your luminosity will be constant. But if you are a brown dwarf, depending on your mass, and this is decreasing mass here, your luminosity will get lower and lower and lower as you age. So this is a simulated color magnitude diagram, which we expect to get with JWST in 47 tuck. So we put the SMC in just to make sure that we remembered the SMC, that they wouldn't think, oh, they're putting the SMC in. So this is the SMC in the same filters. So that's to be ignored basically from here, but it doesn't, as you can see, doesn't affect the brown dwarfs. So this is the cluster, and this is sort of the end of the usual main sequence. These stars are deciding what they want to do, be brown dwarfs or not, and then the brown dwarf sequence basically starts over here. So the interesting thing about a diagram like this is the brown dwarf cooling sequence for clusters of simulated clusters 11, 12, and 13 gigayears. And this is the cumulative distribution of the number of stars. And you can see it in the diagram. You don't have to look at the distribution. That below about 14th magnitude, when they cool, you have less and less stars below about 14th between 14th magnitude on down when you get older, and you can see that it's reflected in that. So the white dwarfs cool, and beyond some magnitude, you can use that as a very nice age discriminant in the cluster to decide the age of the cluster. And here's the cumulative distributions of the number of distributions. Okay, we thought we would make a picture. You want to see a JWST image? Well, here's your first JWST, or one of your first JWST images. This is a simulation of what 47 Tup would look like. And there is a star here, and that's a faint white dwarf. And there is a star here, which you probably can't see, and that's a very low luminosity brown dwarf. But that's what a JWST image, a deep JWST image will look like in 47 to come. Okay, so the new future begins in May 2019, and I hope people are gearing up here to apply for time on it, because if everything goes well, it will be as spectacular a telescope, I think, as Hubble has been. Thank you.
Yes. Thank you very much. Are there any questions for Harvey?
Regarding debris disks around white dwarfs, I don't know anything about this field, but
Did you say white dwarfs or?
Around, that's what you said. You had possible evidence for a debris disk around a white dwarf, and
Yes.
So what?
Let's
Yes,
say
yes. Okay. So clearly, metallicity is an issue because, but 47 Tech is fairly high metallicity.
Is high metallicity.
But the other issue is the environment. And what are there models showing that planets or asteroids would survive existence around the main sequence star in a globular cluster?
Yeah, I mean, there's lots of people have done lots of models for that, and it depends. There's a recent paper by Scott Tremaine, for example, a nice dynamical paper that claims that hot Jupiters could survive can be manufactured and survive in a globular cluster interior. So there's papers like that. There's other people that say that it depends on how the initial disk, the protoplanetary disk forms. It could be disrupted, or the environment. It's easy to disrupt it because there's a very high stellar density in the environment. There's papers on both sides. The crux of it is that there have in fact been observations of transits in clusters, not globular clusters, but in open clusters. There's 2 clusters in the Kepler field, and there's been some transits that have been found, in those clusters. There has been no evidence for planets in globular clusters. There was the big Hubble survey a decade or more ago by Gilliland and his group that found no transits in the core, but there's some issues with that. So I think there are some theoretical arguments that suggest you could have planets forming, that the environment is not so harsh, and it also depends exactly how the planets form, right? I mean, if they form by accretion, whether the disk whether you form them by a disk instability or you form them by accretion of planetesimal and so on. So the theory papers that I've read seem to go both ways. So I don't think there's any strong theoretical reason to say there's no hope for planets and globular clusters. So I think it's an experiment that should be done, irrespective. You know, we should never base our observations on theory.
No.
Harvey, you didn't show us any luminosity function, white dwarf luminosity function.
White
must
dwarf
have-
luminosity
For-
function?
Yeah, you don't have any for us
In
to consider.
JWST?
No, well, you'll have one for JWST, but you already have one from the Hubble data. Yeah.
Oh, yeah, we have lots of them from
Lots of
Hubble.
them. And
No, I don't have, I mean, I have other presentations on my, we'll talk privately, I can show you them after. Yeah.
Are there any other questions, including the remote sites? And I do apologize if you had been muted earlier. So if you also have questions for Chris and you were previously muted, please feel free to speak up. All right. Thanks. It is lunchtime, yeah. Well, thank you very much for allowing me to share some things that are